Okay, welcome back to Nick's Algebraics. Today, I'm going to show you guys how to solve logarithmic equations. By the way, I put the blank and filled out guided notes in the description so you all can follow along if you want. So let's start off by asking ourselves, what is a logarithmic equation? So a logarithmic equation, let me highlight this because it's important. A logarithmic equation is an equation that includes one or more logarithms involving a variable. So the definition is pretty much in the word. You're taking like the log of a variable, and that's part of the equation. Before we start solving logarithmic equations, let's review some inverse properties of logarithms. One important thing to note is that logarithmic functions are the inverses of exponential functions. So in other words, exponential functions and logarithmic functions undo each other. So if you have b to the power of x and you want to get rid of the base, you want to get rid of the base b, what you need to do is take log base b of b to the power of x. And what will happen is the log base b and the base of b will cancel out and you'll just get x. So that's what's happening right here. And if you have log base b of x and you want to get rid of the log base b, you need to exponentiate the log base b of x using base b. So that's a fancy word, exponentiate. So that just means that you're raising log base b to an exponent with a base of b. So what's going to happen is the base b and the log base b will cancel, and you'll just get x. So that's what's happening right here. So we're going to be using this property today because we're solving logarithmic equations and we're trying to eliminate the log. So basically, in summary, to eliminate the base, you have to use logarithms, and to eliminate the log, you have to use exponentiation. You have to raise it to an exponent with some base. So let's do an example of this. So we have to solve this logarithmic equation. We need to figure out what x equals. The first thing we should do for this problem is let's just deal with that 2. I want to get rid of that 2. So let me divide both sides of the equation by 2. So when you do that, you're going to get log base 3 of x plus 1 equals 4 divided by 2, which is 2.
What was the point of designing the problem to just have an extra factor to cancel out at the beginning? Why would you bother designing it this way?
Just to trip people up, some people start using their log properties. Like some people get that 2 and they make it the exponent, which is valid, but it's going to make the problem longer to solve. It's going to make it more difficult. So I purposely put that 2 in there just to emphasize that you should not be using the power property of logarithms here. We have to just divide by 2, and that'll make our lives much easier. So yeah, great question. I'm going to talk about the log properties after this problem. So we have log base 3 of x plus 1 equals 2. So again, I want to solve for x. But the problem is that log base 3 is in the way. So how do we eliminate that log? We have to use one of the inverse logarithmic properties. We have to use this property right here. We have to use exponentiation. So what I'm going to do is I'm going to exponentiate each side of the equation using base 3. So I'm going to raise this to an exponent with a base of 3. So 3 to the power of log base 3 of x plus 1 equals 3 to the power of 2. So that's that step. I just exponentiated each side of the equation using base 3. And what's going to happen is using this property right here, this inverse property, the 3 and the log base 3 are going to undo each other. They're going to cancel out. And you're going to be left with x plus 1 equals 3 squared, which is 9. So if x plus 1 equals 9, what does x equal? Yes, 8. I felt like Dora the Explorer for a second. So yeah, we get that x equals 8. That's our solution. And you can plug 8 into the original equation and you'll see that it checks out. So that's it for example 1.
I disagree. That's not the end of example one. I think you should have brought the two as an exponent, made it a quadratic, and made it way more complicated.
Oh my gosh. That's the true spirit of the Nick's algebraic subscribers. You gotta, think about the alternative ways of solving the problem, even if it's more complicated.
You would have ended up with like an extra solution to the quadratic, and it would have been wrong. And I think it always helps to show that.
Of course, of course.
It's not enough that this answer should be correct. Other answers should be wrong.
Absolutely. So the thing with example 1 is that it involves only one logarithm. But you can see from the definition of a logarithmic equation that I talked about earlier, like a logarithmic equation can have more than one logarithm involved. So what do you do when you have multiple logarithms in one problem? You have to use your properties of logarithms. So let's just review that briefly. So the product property of logarithm says that if you have the logarithm of a product, so log base b of m times n, that equals the sum of the logarithms. That equals log base b of m plus log base b of n. And the next property is the quotient property of logarithms. So this says that if you have the logarithm of a quotient, if you have log base b of m divided by n, that equals the difference of the logarithms. This equals log base b of m minus log base b of n. And the next property is the power property of logarithms. So this says that if you have the logarithm of a number with an exponent, so m to the power of n, that equals the product of the exponent and the logarithm of that number. All right. And then this table right here is the same thing as this table, but with emojis. So I'm catering to the younger audience here. So the product property with emojis says that if you have the log of man and woman, this is like our m times n, then that equals log base b of the woman plus log base b of the man.
Is this how you break up with your girlfriend?
That's right. This is how you separate the couple is using the product property of logarithms. But the cool thing is that if you use this property in reverse, you're bringing them together.
What brings them back together though?
That's a very great
The
question.
man or the woman?
Ooh, that's that's beyond the scope of the video. I'll leave that to the audience to discover. All right.
No, I'm not letting you get off that easy. I'm just pointing out that if you have man plus woman, if you take the log of that side, it's addition. It doesn't distribute the same way a product does. Uh, so this is mainly only useful for breakups, I think.
Especially the divorce rate these days.
Yeah, unfortunate.
I'd also like to point out that your second, the quotient property, is very anti-imperialist of you, which is not necessarily a bad thing. It's just letting that be known.
Of course, thank you. So the quotient property in emojis says that if you have the log of a king, where you can treat the crown as like the numerator and the boy as the denominator, that's like the m over n. then that equals the log of the crown minus the log of the boy. So there you go. That's the quotient property. And lastly, one of my favorites with emojis is the power property. So if you have the log of the smiling sweaty emoji, then that equals the sweat times the log of the smiling emoji. So this is like the m to the power of n and the exponent moving out of the log. So yeah, that's the log properties with emojis.
That one is so clever.
Thank you. Yes. So hopefully people remember these properties better because of the emojis. Let's move on to example 2. So again, we're solving a logarithmic equation. We want to solve for x. And notice that for example 2, the log has no base, like explicitly written out. So does anyone know what the base of this log is?
And
Yes, 10.
So would you say mathematically that logarithms are based?
They're very based. Even if the base is not written, logarithms are based. So this is log base 10. So this is known as a common logarithm. A common logarithm is a logarithm with base 10. And log base 10 pops up so much that we don't even write the 10 and we just write log. So, like I said earlier, there's multiple logarithms in this problem. It's not like example 1 where there was only one log. So what we need to do is we have to use our log properties. Like to solve this equation, we need to condense the logarithmic expression on the left side of the equation. So we need to write 2 times log of x plus log of 4 as a single logarithm. And we do that using our log properties. So what I'm going to do is I'm going to start off by using the power property of logarithms. So this is like the sweat. And what I'm going to do is I'm going to make that the exponent. So I can write this as log of x squared. And then I'm going to write the rest down. So log of 4, so plus log of 4 equals 2. All right, so that's the power property. And we're adding up 2 logs. So what property should we use now to combine these 2 logs?
The breakup property.
the reconciliation property.
Yes, there we go. We're going to use the the product property. So, because the sum of the logarithms equals the logarithm of a product. So this equals log of 4x squared, and that equals 2.
Do you have something personal against parentheses, or do you just like to give your viewers anxiety?
I like to keep my viewers on edge. That's a good point. So you could use parentheses here if you really want to make it very clear that you're taking the log of this entire quantity, but it's not too necessary because it's kind of already pretty clear. But definitely if you're taking the log of a sum, if you're taking the log of like x plus 1, then yeah, 100% you need to use parentheses to make it very clear you're taking the log of this quantity x plus 1. Because if you don't put parentheses, it's going to look like you're taking the log of x and then just adding 1 to that. But for products, it's a little less necessary. But I'll include it just for you.
I've had a professor who would write logarithms, like write a logarithm and then square without using parentheses. So it looks like the logarithm is being squared, not the inside of the logarithm. And it made me very angry.
Oh, interesting. Oh,
That's it. It's interesting.
yeah, that's all I gotta say.
No vow to correct your behavior and like stop the spread of misinformation. Like are you not part of the problem by perpetuating the cycle?
No, it's okay. It's just interesting. So now, just like last time, again, we're trying to solve for x, so I need to get rid of this log here. So I need to exponentiate both sides of the equation using base 10. So 10 to the power of log of 4x squared equals 10 to the power 2. So that's what the fancy word for it is, exponentiating both sides of the equation. So I'm raising both sides to an exponent with a base of 10. And what's going to happen is because of this inverse property I talked about earlier, the the 10 and this log base 10 right here, they're going to undo each other. And you're going to be left with 4x squared equals 10 squared, which is 100. And this is pretty easy to solve now. So I'm going to divide both sides by 4. So I get x squared equals 25. And I'm going to take the square root of both sides of the equation. And I'm going to get x equals plus or minus 5. But there's a bit of a problem here because if you're checking your work and you plug in -5 into the original equation, you're going to get 2 times the log of -5. So when you're trying to find the value of log of -5, you need to ask yourself 10 to the power of what? Here, I'll use u. 10 to the power of what is -5? Because remember, a logarithm is an exponent. You have to ask yourself 10 to the power of what exponent is going to give you -5? And the issue is like 10 to the power of a positive number, that's going to give you a positive number. It's going to give you something greater than 0. So that's not going to give you -5. And 10 to the power of a negative number, that's also positive. Like, for example, 10 to the power of -1 is just 1 over 10. So it's still a positive number. It's a small positive number, but it's still positive. And then 10 to the power 0, because that's neither positive nor negative, that's just 1, which is still positive. So 10 to the power of any real number is greater than 0. So there's no real number that 10 to the power of that number will give you -5. So the logarithm of a negative number, such as log of -5 that we saw earlier, is not defined in the real number system. So this is because a logarithmic function like log of x is only defined for positive values of x. So that means -5 is an extraneous solution. So we're going to exclude it. And our only solution is going to be +5.
So can you scroll to the top to this problem? I like to point out that once again, you like to use unnecessary twos. You could have written log 4 as log 2 squared, put the 2 in front, and cancel the 2 from every term. Just saying.
That's
Could have done
true.
that.
That's also very valid. That's actually a really good idea.
Also, I know you know I was thinking of it. Complex numbers. You
Yep.
can you can come up with some crazy answers to negative logarithms, but I'll leave it at that.
That's absolutely right. You can do some stuff with logs of negative numbers, but that's beyond the scope of this video. So maybe another video I'll talk about that since this is for the Algebra 2 audience. All right, let's do example 3 now. So again, we're solving a logarithmic equation. This is the same idea as last time because we have 2 logarithms. What I need to do to solve this equation is I need to use my log properties. And to use my log properties, I need to get all the logs on one side of the equation. So I'm going to subtract log of x minus 2 from both sides of the equation. So I'm going to get log of 7x plus 1 minus log of x minus 2 equals 1. So now that I have the logs all on one side, I can condense this logarithmic expression using the quotient property of logarithms because we're subtracting the logs. So I can write this as log of 7x plus 1 over x minus 2, and this equals 1. So we have a single logarithm. I'm trying to solve for x. I want x by itself, so I need to get rid of this log. So what do I need to do? What's the fancy word?
Exponentiate.
Yes, we need to exponentiate both sides of the equation using base 10. So I'm not going to show it this time, but like it just, this is what's going to happen. 10 to the power of log of 7x plus 1 over x minus 2 equals 10 to the power of 1. And then the 10 and the log base 10 will cancel. So you're just going to be left with 7x plus 1 over x minus 2 equals 10 to the power of 1. So 7x plus 1 over x minus 2 equals 10 to the power of 1, which is just 10. Now to solve this, what do you guys think I should do now that the log is out of the way? We need to,
Cross multiply.
yeah, I was just gonna say multiply both sides by x minus 2, but that's gonna be the same thing as like cross multiplying if you treat the 10 as a 10 over 1. It'll be the same thing. So yeah, multiply both sides by x minus 2. You're gonna get 7x plus 1 equals 10 times x minus 2. So this is like a 7th grade equation now, a pre-algebra equation. So I'm going to distribute this 10. So I'm going to get 7x plus 1 equals 10x minus 20. And what I'm going to do is I'm going to get the variable terms on one side, the terms with x in it. So I'm going to subtract 7x from both sides. You'll get 1 equals 3x minus 20. And I'll add 20 to both sides, and you'll get 21 equals 3x. And lastly, divide both sides by 3, and you'll get that x equals 7.
Once again, I feel like there was a better way to do this, in my humble opinion. Just exponentiate both sides in the very first step, and I think it was a little bit nicer, in my opinion.
Let's see. Let me write that down actually. So you want to do 10 to the power on that side. That'll just give you 7x plus 1 equals 10 to the power of log of x minus 2 plus 1. Oh, and then you want to like split that up and I'll
Yeah, you can bring that 10 down as a, basic exponent properties. I think this saved some division that looked ugly. But yeah, this is just my preference to solve it.
wow, that does save us a couple steps.
Of course.
So yeah, if you don't want to use your log properties, that's a good way of doing it. You can exponentiate both sides from the very start and use your exponent properties. I like that.
I feel
That's
like there's a lot of different ways to solve these types of equations. I think we should encourage all methods, except for yours.
of course, yeah. Anyway, let's do example 4 now. This will be our last example. So for example 4, notice that instead of log, we have something called ln. Anyone know what that ln means?
It's a logarithm of base e, Euler's number.
That's right. This is a natural logarithm. A natural logarithm is a logarithm with base e. Remember, e is the irrational number that approximately equals 2.718. So log base e pops up so much that we just write ln for short. So what I'm going to do is using my log properties, I can combine these two logs using, the quotient property of logarithms. The difference of the logarithms equals the logarithm of a quotient. So this equals natural log of x squared minus 25 over x minus 5. And on the right side, it's the same thing, natural log of the square root of x. So we're trying to solve for x. I need to get rid of the log, the natural log specifically. So what do I need to do? What's the magic word?
Exponentiate with base e this time.
Absolutely. So base E, and the natural logs will cancel out very nicely. And you'll just be left with x squared minus 25 over x minus 5 equals the square root of x. What can we do with x squared minus 25 divided by x minus 5? Is there anything in algebra that can help us simplify over there?
So what you could do is a difference of squares factoring in the numerator, and that should do some cancellation.
Absolutely. So we know that when you have a difference of squares, when you have a squared minus b squared, That equals a plus b times a minus b. That's what it is in factored form. When you use that on x squared minus 25, you're going to get x plus 5 times x minus 5 all over x minus 5. And again, this equals the square root of x. So you can see the x minus 5s are going to cancel out. And you're going to be left with x plus 5 equals the square root of x. So there's something interesting about this equation. Like this equation is saying that when you take the square root of a number, you're going to get that number back plus 5. So the issue is that most of the time when you're taking the square root of a number, you output a much smaller number. Like for example, if you take the square root of 100, you just get 10. You get a much smaller number. The only time the square root of a number outputs a larger number is when the input is between 0 and 1. So for example, like if you're taking the square root of 1/4, like the square root of 1 is 1, the square root of 4 is 2, so you get 1/2. And 1/2 is larger than 1/4, of course. But the problem is that in this problem, x cannot be between 0 and 1. Because if you look over here, if x is between 0 and 1, you're doing x minus 5 inside the natural log. So you would be taking the log of a negative number. So it looks like we have no solution. But let's just continue this problem because I know that most people aren't going to notice that this early. So if you kept going, what you would need to do is you would need to square both sides of the equation because we're trying to get rid of that square root. So if you square both sides, you'll get x plus 5 squared. And when you square the square root, you'll just get x. So to square x plus 5, we can't just distribute the squared. It's not x squared plus 25. We have to use the FOIL method. Like this equals x plus 5 times x plus 5. And we need to FOIL. So if you do first, outer, inner, last, we have first is x squared. The outer and the inner is 5x plus 5x, so that's 10x. And 5 times 5 is last, that's 25. And we have a quadratic equation. So let me just get everything to one side of the equation by subtracting x from both sides. And you'll get x squared plus 9x plus 25 equals 0. And what I'm going to do is I'm going to take a look at the discriminant for this quadratic equation. So remember the discriminant is b squared minus 4ac. I'm just going to do this on the side. In this case, a is 1 because it's 1x squared. B is 9. And c is 25. So b squared minus 4ac, it's 9 squared minus 4a, which is 1, c, which is 25. So 9 squared is 81, and 4 times 1 is 4, and then times 25, that's 100. And 81 minus 100, I don't even care what that is. The only thing I care about is that it's less than 0. It's negative. And when the discriminant is negative, that means that this quadratic equation has no real solution, just as I thought. All right, so that's the last problem, guys. That's all I got for today.
So I pretty much agree with everything in this problem. One thing that you could have done is when you factor x squared minus 25, you could do that in the first step. And then like ln of x minus 5 would have canceled like addition and subtraction style instead of division style. But like, yeah, it's the same thing. Doesn't matter.
Okay, cool.
He agreed with something. I'm shocked.
Yeah, I was a little shocked too.
Wow.
I'm fair. I'm fair. I pride myself in that. When you're wrong, which is most of the time, I'll point it out. When you're right, I'll point out that you're not completely wrong.
Okay, wonderful. But yeah, that's it. So don't forget to like, subscribe, and comment, and I'll see you guys in the next video.